Thanks, everyone. Thanks for the nice introduction. We heard a lot this morning about dark matter, which is the mystery of human behavior. So I'm going to zoom out a little and talk about the dark matter in the galaxy. What is dark matter and how do we know it exists? I'm going to show something that we are all familiar with, which is our own solar system. If this thing listens, there we go. So this chart shows the orbital speed of the different planets as a function of the distance from the sun. You can see I'm a rebel because Pluto is still a planet for me, or this chart is very old. As you all know, the year on Earth is the Earth's orbit is exactly 1 year. That's what it comes from. On Mercury, it's about 3 months. Out to Neptune is about 200 years. So that's a general law of physics. When you have the mass in a system concentrated in a spot, things will go slower, will rotate slower when you go away from the center of mass. So we can ask ourselves what this looks like with the galaxy. We've been making a lot of measurements about rotational velocities in galaxies since the 70s. And if you take it, this is the Triangulum galaxy, which is where this measurement was first made before I was born, but not that long before. This is a photo of the Triangulum galaxy. You can estimate the mass from the light that you see. And you know there is a curve there that shows you the rotational velocity that we expect from the visible disk. So they made the measurement, and this is what they found. Not only were things going like not slowing down, they were going faster, even out to where there was no visible stars, etc. If you've taken a little bit of classical mechanics, you can apply the virial theorem to this chart. You have a factor of 3 discrepancy between the two curves out at the edge. That means there is about a factor of 9 mass that is there. We see the gravitational effect. We're not seeing the actual thing. We're not seeing the light. Person who made this measurement is a woman by the name of Ira Rubin. She died a few years ago. And like irony, the new dark energy telescope that is being built at Gran Sasso is named after her. But dark energy is not dark matter. So anyways, we're going to zoom. I showed you what the galaxy looks like. I'm going to zoom way out and talk about the whole universe. This is a picture from the recently released data from the James Webb Space Telescope. You see all those objects in the back that are kind of like red and wiggly. There is a lot of dark matter in this photo, very obviously. We don't see it, but the wiggliness shows that there is a lot of matter between us and the object, even though we don't actually see the matter. So you all know that 14 billion years ago, the universe blew up out of nowhere. And 400,000 years after the Big Bang, what we call the Big Bang, or the beginning of the expansion, there was a recombination event. Basically, there was light produced. That light is still there now. So if I go back here, the previous thing, and look what's behind those red galaxies, what's there, you know, when there are no stars, no galaxies, what I see is a little bit of light. It's in the millimeter wave, centimeter wave, so this is what it looks like in false colors. Basically, there was an explosion. This is warm and cold spots in the explosion that we can still see. They are 3 degrees above the absolute zero. We call this a baby picture of the universe. This is what it looked like 400,000 years after the Big Bang. This is the measurement from Planck in 2000, I'm going to say 13. And if we represent this picture in a unit that's called spherical harmonics, we can use it to weigh how much stuff is in the universe right now. Interestingly enough, you see a 4.9% in yellow there. That's every particle that we ever discovered or ever measured at a collider, a detector, etc. So most of the universe, sorry, this was outside the newspaper stand. They described it very well. Most of the universe is missing. We don't know what it's made of. We have about 27% to 30% of dark matter, 5% is the stuff we know, and everything else is dark energy. The first time this was attempted, this was measured, the different fractions. I was taking a gap year to do research between my master's and my PhD. Let me tell you, that was a great time to get into physics. Okay, what is dark matter? Spoiler alert, we don't know, and I call that job security, but anyways. I said earlier, all the particles we know, there is 13 of them, no, 17 of them. This is a new chart because it includes the Higgs boson, so it's after 2013. We're going to compare this list with the known properties of dark matter. Dark matter has gravitational interaction because we see it like rotate the galaxy, hold it together. Because it holds the galaxy together, it has to live not a fraction of a second. This gets rid of like 70% of the particles that we know. And then it cannot be hot or light or slippery. I'm talking now about neutrinos. Neutrinos are elementary particles. For example, the sun sends out, we get from the sun 100 billion neutrinos per square centimeter per second. So I don't know where south is, but if I put my hand, it's going to be like million billion neutrinos per second. They're very slippery. They go through everything. They cannot hold the galaxy together. So remove the neutrinos, and then I'm left with the electron, up and down quarks, which make up protons and neutrons. So I'm left with the stuff we're made of. We interact with light. We don't shine, but we shade, or we reflect. That's why you see me right now. So it's not it, because otherwise we would see it. And so we're done. We don't have any particles left. Like I said earlier, very good news for a particle physicist, because it means there are new particles we haven't found yet. So what do we know about dark matter? Well, there is a lot of it. We use the iceberg thing to describe visible and dark matter. It was formed during the Big Bang, that's what we think, because during the Big Bang there was basically infinite energy, so you could make an infinite amount of, an arbitrary amount of anything. So to make a lot of anything, you take the Big Bang. Now we can rewind the movie to the Big Bang, of the Big Bang to about 1 second from the very beginning, and in that 1 second, we actually see it interact with regular matter. So, let's see if we can make it interact with regular matter again. So that's what we're trying to do. This is called direct dark matter detection. It has very cool detectors. I'm going to show you a lot of pictures now. The idea here is that dark matter particles will interact with the atomic nuclei. And the recipe is build a massive tank or a massive tower of nuclei, hide it deep underground, wait for the dark matter particle to bump into one of your nuclei, and it's going to be extremely rare. Look for the recoil on the nucleus, so the tiny vibrations from the nucleus that has been hit by dark matter. You should have screamed when I said underground. Why are you hiding your thing underground? This is a GIF of the aurora borealis from space. This is what our atmosphere looks like. Most of the time, we don't see the charged particles with our eyes, but like we're being bombarded by cosmic rays. If I put a detector this big here, the ultra-sensitive detector, that's all we're going to see. It's going to light up like a Christmas tree. So what we do is we bury it under a mountain. This is an example of what they do in Mont Blanc. What we do is our experiment is in South Dakota, in the former Homestake mine, a mile underground. If you've seen the TV show Deadwood, or if you know of the Hearst family, that's the mine that we're talking about. No gold, just dark matter. My experiment is called LZ, acronym of acronyms. I'll apologize, I didn't pick the name. I can't even say it, to be honest, but anyways. This is in South Dakota. Great place to visit. It's not known as a tourist destination. It is awesome, especially in the summer. You can see at the top of the mountain there, that's the head frame. The cable is about 6 miles long. You can go way deeper than where we are. They started digging from the top, and then it caved in. We call that the open cut. So that's what it is. Like I said, if you grew up in Europe like I did, and you watch movies about America, the Wild West, that's what it is. There is mining, there is like, Wild Bill, all these people. Calamity Jane is buried in Deadwood. So great place to visit. So this is how the detector works. It's a bucket of liquid xenon containing 10 tons of the stuff. Liquid xenon is very compact, very dense, so it's about yay big by yay big, 5 by 5 feet. It packs a lot of mass, 10 tons in this much. I don't weigh 10 tons, I promise. So the funny thing is that we measure the recoils, and we measure it through light. So basically what happens is I have a dark matter particle, bumps into a xenon atom. Xenon atom gets very excited. Its electrons start jumping up and down, and when they jump up and down, they emit light, and we measure with photodetectors at the top and bottom of the bucket. Then we apply an electric field, extract the electrons. Some electrons get knocked loose. We extract them. They go to the top where we have a thin layer of gas, more light, we detect it again. So it's kind of fun that we detect dark matter using a light signal. How do you build a massive tank of nuclei? Take a lot of photos because those things look great. We have photodetectors. They're 3 inches across. This was 30 years of work to build those things that work in the cold, ultraviolet, low radioactivity. We have a lot of them, like 500 of them. And then we built a bucket. In the bucket, you make it of very reflective material so that you collect all the light. And it was designed by one of our engineers who, after the fact, we found out was a Lego fan. And that's basically how we built it. We built it like a Lego bucket. It took about 3 weeks. It was a pretty quick process to build once you had it. Then you mate the the light sensor arrays to the bucket. That's the finished product. Then you put it in a, sorry, I should point over there. You can't see the screen where I'm pointing. Roll it to the side and bring it down. That's the head frame where the cable goes. That was October of 2019. There was a lot of snow already. And this is the detector at the end of its journey down the shaft. It was hung down below the cable. It wouldn't fit in the cage, in the elevator cage. And they lowered it very slowly. It took about 2 hours. When we lower humans, it takes 11 minutes. So that was a priority. And if you ask us how we settle on this detector size, oh no, I forgot, never mind. Sorry. Here's a question. You saw everybody wearing like clean room suit. What are we trying to do? Well, everything's radioactive. Spoiler alert, we are very radioactive. The air we breathe is a little bit radioactive, which is how carbon-14 dating works. Potassium is a little bit radioactive, but if you don't have potassium, your heart stops. Nothing to be scared of. But if we don't build things way less radioactive than we are, we're just going to see the materials itself. So we made it super clean, put it a mile underground to suppress stuff from the atmosphere. All our materials are between 100,000 and 1 million times cleaner than regular, than what we're made of, which means we had to invent new materials, but that's a different story. And even then, we get about 50 counts per second in our detector of background, stuff that is not dark matter. Or 1 billion counts per year, or 5 billion, or 1 petabyte of data a year, 5 petabyte total in our search. How does this compare to dark matter? Dark matter is spectacularly elusive. So in a liter of, I should have brought a water bottle, but in a liter of volume on Earth, there are always about 3 dark matter particles. We're slamming, again, towards the dark matter halo, so it's streaming through us at 150 miles per second. So in my bucket, there is 1 billion of particles that go through every second. Of these, if we're very, 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 very lucky, we will measure a handful a year, 5, 6, 10, which is a very small number. And like I said earlier, this is like 1 billion of background particles per year. So this is an extreme needle in a haystack problem. We heard this morning, and the haystack that was full of needles, mine is not, so this is how we feel about it. And so how does this work? Well, for starter, the xenon is very dense. Regular stuff will interact multiple times. Dark matter will interact never, or at most once. So we throw out everything that interacts more than once. And then that's already 95% of the interactions. Then we do some quality cuts for the things that don't leave enough energy to tell what they are. And then, because xenon is so dense, it's basically a wall for gamma rays that come from the cavern, from outside, from the detector material. And you see there that all the radioactivity shows up on the edge. So if we take the inner part and then do some quality cut, we're already down by a factor of 1 million. And then what we do, I showed you earlier that I have the drawing. We measure the interaction twice. The first time when the nucleus starts getting excited and the electrons jump up and down, and the second time when the electrons are extracted, the electron that gets loose. For dark matter or neutrons, the number of extracted electrons is much smaller than from everything else. So using that technique, we get rid of another 99.5% of the background. So we're left with 10 to the minus 9 event from what we started for, so a factor of 1 billion rejection. I'm making it sound easy, but it requires a couple of supercomputers. This is the newest one that we have at NERSC in Berkeley. And it required us to build the experiment in software between 3 and 5 times, depending how you count. So the last 5 years, while we were building and installing the detector, we did those things that are called MDC 1, 2, 3. So we build the detector in software, build the dark matter in software, threw all the dark matter and all the background signal at it, always simulated and practiced with it. So much so that when we actually took data in the spring of last year, we had results in like 2 weeks. We submitted to the journal 5 weeks later. Like all my students told me, this was way easier than what you had us do the last 5 years. So that's what we did to prepare. We had first light, like a telescope, although this is not really a telescope. We leveled the detector because there is a thin layer of gas on top, so you have to center the liquid level within the electrodes. You know, we had little things to move it up and down. Very importantly, we can put radioactive stuff or shine radioactive stuff to the body of the detector to know what the signal looks like. The orange, the lower band, is where dark matter should show up. The blue is where all the external radioactivity should show up, all the radioactivity. So this is, you know, when you shine a radioactive source, which you know mimics the signal in the background. When you really turn it on, it looks like this. The detector screams at you, and then we do the cleanup that I mentioned earlier. For example, if you do the radial distribution, so x-axis is the radius, the distance from the center, and then y-axis is the depth, all the background shows up on the edge. So if you make a quiet box inside, you get rid of like 95% of the backgrounds, and all the selections I showed you earlier. So data cleans up nice. I forgot to tell you, this is a data science conference. I want to say there are fancy algorithms that we use. Because these things are like 1 in a billion, what we use is the same techniques that are used at the data centers for intrusion detection. You know, there are very few hackers compared to the number of users, so we borrow their techniques. So this is a clustering, anomaly detection using clustering, which comes from Google Cloud. And this is, sorry, went the wrong way. And this is from my postdoc's PhD thesis. It's kind of the same plot, but not with the same color scale. And maybe you see there that there are smudges of blue and the stuff underneath. Those are detector anomalies that could trick us into thinking we saw dark matter, but didn't. And so it was fun with the same technique that is used all over with, you know, in AI. So like I said, the data set cleans up real nice. So the red band here, where it says NR band, is where the dark matter should show up. And the gray band is when we do all the cleaning and we only have the good background events, the ones that are nominal, let's say. You see that the red band is pretty empty. And in fact, we fitted this, and the best fit was 0 dark matter interactions at every mass. I did not explain what this chart is. I don't think it matters. I think the interesting bit is like, okay, the red bands is where we expect dark matter to show up, and it didn't. Disappointing, but like I said, job security. And also, we like to say we found nothing but better than everybody else. And so, if you look in a space for dark matter and you don't find it in that space, that tells you a lot about what dark matter looks like, because it's not there. You know, like when you lose your keys and you empty your bag and it's not in your bag, you're like, okay, maybe it's on the counter. Same thing. So purple is better, so we're going down, and the curve there, you know, those are our competitors, and you see every year there is a new line of a different experiment that says, not here, not here, not here, so we're going down. Like I said earlier, job security, so we have like 5 years to look for this, so we're going to go down more. And then in orange is when our search will be done, because we have too much backgrounds that we cannot discriminate against. Like I said, 5 petabytes of data. If you have brilliant algorithms that you want to use for ultra-rare anomaly detection, talk to me, we can make a deal, I'm Italian. I can trade data for algorithms, etc. So I want to acknowledge that this is a large effort. My team, this is a photo from right before the pandemic, 2019. We were all in South Dakota in the summer. We're going back this summer, finally, after 4 years. It's 250 people from 3 continents, 35 institutions, lots of funding agencies. I love that governments all over the world want to put money into figuring out what reality is made of. And then it's not just us. If you zoom out, there are maybe 30, 40 teams that are looking for dark matter right now in 3 underground labs in the American continent, 3 underground labs in Europe, 3 in Asia, et cetera, and there are like 30, 40 teams. I started doing this research in 2006 when there were like 50 people or less working on this problem. Now it's like 2,000, something like that. It exploded. 30 groups, we haven't found anything. I'm just gonna say this photo is, if you see it, it's a little bit bright, but it's the Milky Way observed from New Zealand. New Zealand is important because the galactic center cannot be observed from the northern hemisphere. Like where you see that cloud over there to the right, that's the center of the galaxy. And it's shady because there is matter, there is gas between us and the center of the galaxy. So most of what you see in this photo is dark matter, but you don't see it because we don't have dark matter eyes. And it's out there, there's a lot of it, it's waiting to be found, it's hiding in plain sight. If you guys, I see a lot of people younger than me here, if you want to do a career change, if you're looking for a dissertation, there will be work to do for the next 20, 30 years in here. Hopefully we will find it, but we may not, so please come work with us.